We can see the application of the ideal gas law in a problem like this one, trying to find the volume of 1 mole of xenon gas at 0 degrees Celsius and 760 millimeters of mercury pressure. So we're going to start from the equation PV equals nRT, and since we're solving for volume, I recommend that you solve for V before you plug in any numbers. So do the algebra on the variables, and now plug in your N. The number of moles is 1. Gas constant R. Temperature T. Remember, you have to cancel out your units, and notice in the gas constant we have Kelvin instead of degrees Celsius. So we never use degrees Celsius. We have to convert to Kelvin by adding 273.15, and 0 degrees Celsius is 273.15 Kelvin. The pressure was given as 760 millimeters of mercury, and notice the pressure unit in the gas constant is atmosphere, so we need to convert those millimeters of mercury into atmosphere, and the conversion is 1 atmosphere equals 760 millimeters of mercury. So if we double check our units, mole cancels with mole, Kelvin cancels with Kelvin, millimeters of mercury cancel, atmosphere in the bottom cancels atmosphere in the top, and we're left with the unit we want for volume, which is liters. So the volume works out to be 22.4 liters. And the reason that we go through this problem is this temperature, 0 degrees Celsius, and this pressure of 1 atmosphere is called standard temperature and pressure, STP. So 22.4 liters is the volume of 1 mole of an ideal gas. So this is a nice conversion between how much volume and how many moles the gas will occupy. This only works at STP. If the temperature is different, if the pressure is different, then the volume is no longer 22.4 liters. Notice we never used the fact that this was xenon gas. If this had been helium or argon, we would have gotten exactly the same answer. So we can use this as a conversion between moles and liters, and it doesn't matter what the identity of the gas is. The identity does matter in a problem like the next one when you're worried about mass, because the molar mass of nitrogen is different than the molar mass of xenon, for example. So this next question, if we want to find the mass, we're going to do this in 2 steps. First, we're going to solve for the number of moles N, which is PV over RT, and the pressure is 13,000 torr, and we want to convert that to atmospheres to cancel out the unit atmosphere in the gas constant, and the conversion is 760 torr is equal to 1 atmosphere. A torr is the same exact thing as a millimeter of mercury. It's just another name for millimeter of mercury. V, the volume, was 50 liters. Gas constant R, and then the temperature 22 degrees Celsius, so we're going to add 273.15 to get that into Kelvin. You'll always know your units are correct if you look at the units of the gas constant. Liters, the volume has to be in liters. Pressure has to be in atmosphere. Moles is what we're looking for, and Kelvin tells us the temperature has to be in Kelvin. So when we solve this equation for N, the number of moles is going to be just over 35 moles of nitrogen gas. And remember, nitrogen is a diatomic, N2, it's not just N. And then part 2 to this problem, we want to figure out how many grams of nitrogen we have. So this is where the identity of the gas matters. We have 35.3 moles of nitrogen, and 1 mole of nitrogen, we use the periodic table to find the molar mass of 28.02 grams, gives us an answer of 989 grams of nitrogen.